All right, so 6.5 trigonometric equations. Looking at this equation right here, we want to solve for x. We have 3 sine x minus 2 equal to 5 sine x minus 1. So just like when dealing with algebra, let's take on the same thought process, same mindset. All of our terms with sine x, we're going to bring to one side of our equation. All of our terms without it, we're going to take to the other side. So notice I subtract 5 sine x from both sides of the equation. And that gives me negative 2 sine x minus 2 equal to negative 1. Now I need to take the negative 2. Oh, I had my eraser still on. Take the negative 2 to the other side. So I'm going to add 2x, not 2x, add 2 to both sides. And that will put me at negative 2 sine x equal to 1. Now I need to divide both sides by negative 2. And so now I'm sitting here with sine x equal to negative 1/2. And so we want to answer the question, when is sine x equal to negative 1/2? Or in other words, if we apply sine inverse to both sides of our equation so that sine can cancel, leaving us with just x on the left side. And then on the right side, we're looking at sine inverse of negative 1/2. All right. So we want to know, when is sine negative 1/2? So if we pull up the unit circle, should have already had it up. And of course, it's taking a little while. Okay, why is it not popping up? Give me 1 second. There we go. All right, so here's our unit circle. We want to know when is sine negative 1/2. And so remember, sine is our y. The y component is going to let me draw on it. Yeah, there we go. So sine is my y component. So here we have 1/2, positive 1/2 is y. And so just making sure we remember cosine. But it won't let me draw. There we go. Cosine is x, sine is y. So we want to look at the different places where we have sine as negative 1/2. So that's right here and right here in those 2 spots. So that's at 7 power over 6, 11 power over 6. Okay. Let's go back to our notes. And so that's why we have 7 power over 6 plus 2 n pi, because we're talking about for every rotation, every full rotation that will occur. So that's why it's 7 power over 6 plus 2 n pi, and then 11 pi over 6 plus 2 n pi. Remember, your periods for sine and cosine is 2 pi. So for every rotation this occurs, sine is equal to negative 1/2. Okay. All right, looking at the next one. Making sure my share is on properly. Yes. So now we have tan of 3x equal to 1. Also, we have this initial condition setting what we want x to be. X is going to be in between 0 and 2 pi, so that's going to matter when we get to our final answer. That was not the case in our first problem, so that's why we had to do these periods, okay, to cover all scenarios of our answers. Here, our answers will not exceed 2 pi, okay? So apply tan inverse to both sides. And so tan cancels on the left, leaving us with just 3 pi. Just trying to get rid of that. And so we have 3x equal to 1/4 plus n pi. And I was doing this initially because I wasn't considering the fact that we have 0 to 2 pi. Nah, I can leave it because at the end it will give us our options. So no, let's leave it. So I'm good to go. And then, so what we're going to do is we want to still solve for x. So let's apply 1/3 to both sides. If my stuff will come back up. There we go. Apply 1/3 to both sides. And that gives us pi over 12 plus n pi over 3. Okay. So now, the reason why I went ahead and left that is because we want to cover all scenarios in which this occurs within 0 and 2 pi. Okay. All right. So now just generically, we know tan over here. I was talking about how tan inverse of 1 will give you pi over 4 and 5 pi over 4. But we had to consider, when you do pi over 4, that covers 1. And then when you do n pi, which is periods of your tan's period is going to be pi. Cosine and sine's period is 2 pi. So that covers, this pi over 4. All right. So I don't have to write this and this, just do the pi over 4 and then write the period. Okay. And that's the diagram I was giving right here as well, just re-emphasizing that. So now, because of 0, x being in between 0 and 2 pi, the answer is desired should be specific, not a general solution solving. So if it didn't give us that 0 to 2 pi, I could stop right here. But because it doesn't, now I need to go plugging in values for n and figure out how many of my answers will actually fit this description. So I should have started with 0, because remember, we're talking about 0 to 2 pi. So plugging in 0 for n. So 0 pi over 3 is just 0, so that's just 12 pi. Then plug in 1. That's 12 pi over 12 plus pi over 3. Do your fraction work, multiply top and bottom by 4 in order to have common denominators. That'll be 5 pi over 12. Do the same thing for 2. Once again, multiply top and bottom by 4. End up giving you pi over 12 plus 8 pi over 12, which is 9 pi over 12. Now, you want to know when should we stop? Of course, you could throw this answer in the calculator, and if it's greater than 2 pi, then you're gone over. Or you just recognize that 2 pi as a fraction with the denominator 12 would be 24 pi. Then whenever my answer goes over 24 pi, then I know I can't use that and I can use everything else under it. So you can just keep going. Same thing with plugging in 3, multiplying, yep, top and bottom by 4. Once again, that'll give you 12 over 12. That's 13 pi over 12. Multiply top and bottom here by 4. 16 pi over 12. Once you plug in 4 for n, that'll give you 17 pi over 12 ultimately. Here, multiplying 4 to the top and bottom. Make it a little closer. So that'll be 20 pi over 12 plus pi over 12, which is 21 pi over 12. You can reduce that down to 7 pi over 4. I think that was the only one that could reduce. We could have reduced this one as well. But it's good enough. We'll be all right. I guess I can go ahead and write it. 3 pi over 4. All right. Yep. So we got 5 pi over 12, pi over 12, 3 pi over 4, 13 pi over 12, 17 pi over 12, 21 over 12. Take that 3 out, 7 over 12. And then here, when we plug in 6, multiply top and bottom by 4, just like we've done in all the other ones. So we have that common denominator 12. That gives us 25 pi over 12 when we add it together to the pi over 12. That's greater than 2 pi, so we know we cannot use that value. All right. And so that's where we'll stop. Those will be our answers. We have 5 power over 12, power over 12, 3 power over 4, 13 power over 12, 17 power over 12, and 7 power over 4 would be our 6 answers. All right. Okay, so next one. We have 2 cosine squared x plus cosine x minus 1 equal to 0. And then notice here we have the same stipulation of x being in between 0 and 2 pi. So the first thing I did here was factor. So this is algebra. Factor that out, that'd be 2 cosine x minus 1, cosine x plus 1 equal to 0. From there, set both pieces equal to 0. Remember, whenever you're using factoring as a part of your solving, once you factor completely, you can set both pieces equal to 0. Excuse me, I had a sneeze. So solve each for x. So notice here we added 1 to both sides, divided both sides by 2. So we have cosine x equal to 1/2. Then apply cosine inverse to both sides. Cosine inverse of 1/2 would be pi over 3, 5 pi over 3. And remember, you can always lean on your unit circles. So if we go back to our unit circle, we want to know when is cosine equal to 1/2. Here at pi over 3. And here at, where's 5 pi over 3? Right here, 5 pi over 3. Those are 2 places where x is equal to 1/2, where cosine is equal to 1/2. All right. And then, excuse me. And then for the next one over here, solve for x again, subtract 1 from both sides, then apply cosine inverse to both sides. And we want to know when is cosine -1. So cosine inverse of -1. If you go back to your unit circle, cosine being -1 is right here at pi. It's the only place that occurs. And so that's why x is equal to pi. All right. Those are our 3 answers. Okay, next one. 4 sine squared x minus 1 equal to 0. Once again, stipulation in place of what x can and cannot be equal to. So we add 1 to both sides, divide both sides by 4. So once we do that, we're looking at sine squared x equal to 1/2 or 1/4, excuse me. Then take the square root of both sides to get the square off of sine. That's sine x equal to plus or minus square root of 1/4, which then in turn would be plus or minus 1/2. So from there, you take the sine x of 1/2, then sine x equal to 1/2, sine x equal to -1/2, apply sine inverse to both sides. And then once again, you can go to your circle, find where sine, in other words, y, your y component of your ordered pairs is equal to 1/2, and then find where your y components of your ordered pairs are equal to -1/2, and those will be your 4 answers. All right, any problems, any problems? No, I said that like somebody's listening. All right, so the next one, tan x sine squared x equal to 3 tan x. Once again, x is between 0 and 2 pi. So what we do here is go ahead and set one side equal to 0 by subtracting 3 tan x from both sides. Then from there, factor out tan x. All right, so bring tan x to the front, leaving you with sine squared x minus 3 in the parentheses. All right, so tan inverse of both sides. X is equal to tan inverse of 0. So you want to know where tan x is equal to 0. That's those two spots. X is equal to 0 and pi. Then here we take the square root of both sides. Don't forget square root property. So we have sine x is equal to plus or minus square root of 3. And so if you were to try to find this on a unit circle, of course you wouldn't see it. Also apply your calculator to it. You should get an error message or something along those lines. Wherein if you take sine inverse of the square root of 3, square root of 3 is 1.73. So don't forget the range or the domain of your sine is -1 and +1. This goes outside of that. So that's why that doesn't work. So your only answers is pi and 0. All right. I think this is the last one. So we got 2 of them. Okay. I think this is where we stopped at in class. Okay. We have 2 cosine squared x plus 3 sine x equal to 0. All right. So what I did here, in order for me to have all sines, I went ahead and rewrote this cosine squared by using your Pythagorean identity. So sine squared plus cosine squared is equal to 1. So I solved it for cosine squared by subtracting sine squared at both sides. And we have this relationship, cosine squared x is equal to 1 minus sine squared x. And I substitute that in for cosine squared x. So that's 2 times 1 minus sine squared x plus 3 sine x equal to 0. All right, so this is what we have after I distribute the 2. All right. So from there, I just rearranged it in terms of your highest power being first, descending order, just like we would in algebra. So we have -2 sine squared x plus 3 sine x plus 2 equal to 0. And I multiplied each term by -1 because I have a negative sitting in front of my leading coefficient. So like I said, this is just algebra stuff, algebra thoughts. So now I have 2 sine squared x minus 3 sine x minus 2 equals 0. Now factor the trinomial. And so I have 2 sine x plus 1 sine x minus 2 equal to 0. And now I can set each piece equal to 0. So we have 2 sine x plus 1. Solve it for sine x. That'll be sine x equal to -1/2. When you subtract 1 from both sides, divide by 2. Apply sine inverse to both sides. That gives me these two answers, 7 power over 6 and 11 power over 6. And then over here, add 2 to both sides, apply the sine inverse to both sides so that it'll cancel out on the left, leave me with just x. Then applying the sine inverse to 2. 2 is outside of the domain, just like the last one. You know, our domain for our sine is -1 to +1. So that doesn't work. That does not produce a solution for us. So these are our only 2 solutions. All right. Okay, so we have one more. We have sine x minus cosine x equal to 1. We want to square both sides with the anticipation of using sine squared plus cosine squared equal to 1. Remember, I told you that's the one that will always pop up. Pythagorean identity that will always pop up. Sine squared plus cosine squared equal to 1. So we square both sides because in its current state, we really can't do much with it. So we're going to have to FOIL this out. On the right, 1 squared is just 1. But on the left, we have sine x minus cosine, sine x minus cosine. So FOIL that out. You know, sine times sine, sine times cosine, cosine, and negative cosine times sine, negative cosine times negative cosine. And that gives us this result here. So we have sine squared minus sine x cosine x minus sine x cosine x plus cosine squared equal to 1. So I combine my like terms and then group together that Pythagorean identity that I was mentioning. So yep. So I brought these together. Sine squared plus cosine squared would always equal to 1. Add these together. That's -2 sine x cosine x. All right. So adding these together gives me 1. Let me get it back. So this is what we have. 1 minus 2 sine x cosine x equal to 1. Now, continue your solving. You're going to subtract 1 from both sides. That will be -2 sine x cosine x equal to 0. Because the -1 and the +1 cancels on the left, but it also cancels out on the right as well. All right, so now we have this sine x cosine x equal to 0. And then we go ahead and go about solving by doing our sine inverse and our cosine inverse. So sine inverse of 0 is going to be 0 and pi. Those are two places where sine, your y component is 0. And cosine inverse of 0, the two places where that occurs is pi over 2, 3 pi over 2. You know, in your unit circle. All right, so here's a note. Whenever you raise both sides of an equation to an even power, you must check for extraneous solutions. So in other words, these are solutions that will not work. But that's what happens whenever you're raising any equation to the power of an even number. So whether this is trig or just regular algebra, that's something that you always have to check for. Whenever you're raising both sides of an equation to an even power, you have to check for your solutions and make sure they're correct. You could have done everything correct mathematically, and you still come out with these extraneous values. These are the extraneous solutions. These are solutions that will not work. All right. So we go plug them into our original equation. And you see the first one that we try, plugging in 0. Sine 0, cosine 0 are both 0. 0 is equal to 1, which is incorrect, so that doesn't work. Plugging in pi, that ends up working for us. Plugging in pi over 2 works. Plugging in 3 pi over 2 does not work. So only solutions is pi and pi over 2. Those are the two that worked. All right. So that's it. Let me know if you have any questions after you view the video. All right, take care.